Good day. In this video, I will teach you how to find the rotation matrix of an articulated manipulator. Okay, so let's start by getting the equation of our rotation matrix. So this is R03 is equals to the rotation matrices from the base up to the end effector. So R01 times R12 times R23. Okay. So we will derive first the rotation matrix of R01. So a we need a rota a n- rotation matrix, a stationary rotation matrix, and the moving matrix. Okay. So the moving matrix will be based on where does the joint variable of the joint is located. So we are doing the rotation matrix, or we are deriving the rotation matrix of frame 0 and frame 1. Okay? The rotation matrix are 0, 1. So the joint variable theta is at the axis of both z sub 0 and y sub 1. So as you can see, theta 1 is at both the axis of z0 and y sub 1. So what we will do here, we will choose between the two. Okay, so we have here the z rotation. Okay, so the z rotation is the rotation matrix at the z axis. So let's lose the sub 2 first. Okay, so this is the rotation. Then y rotation, if it is rotating at the y axis. Okay, so this is the y rotation. So this is derived. These are derived from the principle of projection. Okay, and using Sohcahtoa in deriving the elements of these rotation matrices. Okay, so we will just choose one of these two rotation matrices. Okay, then we will multiply the chosen rotation matrix to the moving matrix, or to the stationary matrix. Okay, if we choose the z rotation, if we choose the z rotation, it should be multiplied at the left side of the rotation of the stationary matrix. Then if we choose the y rotation, it should be multiplied at the right side of the stationary matrix. Okay. So why do we need that rule? Okay. So z rotation matrix was based from the z sub 0 axis, where z sub 0 is at the reference frame or the base frame, okay, of this mechanical manipulator, while the y rotation was based from the y sub 1 axis, which is located at the frame 1 at the joint 2, at the revolute joint 2. Okay, so based on the principle of projection, the reference frame, okay, this is the reference frame. The reference frame will not move when when there is a change in joint variable theta, just like in our original drawing. Okay, Okay, this is the drawing. This is the principle again of projection. And this is our two frames. Okay, two frames formed by the principle of projection, frame 0 and frame 1. Frame 0 is the reference frame. Frame 1 is the projected frame. When there is a joint variable theta that makes the z sub 1 axis rotate, okay, all of the axes at the frame of frame 1 will move. So the reference frame, the axis of the reference frame will not move, only the projected frame. Okay, so same as here, z0 is the axis at the reference frame. So in reality, it doesn't move when there is a change on the value of joint variable theta. And what is really moving is the projected frame. Okay, so when theta 1 changes its value from 0 to 360 degrees, okay, the frame of frame 1 will move. Okay, will move. It will rotate counterclockwise. Okay, so that's the reason why the rotation matrix must be multiplied at the left side of the stationary matrix if you choose the rotation, while y rotation matrix is the real moving matrix. Okay, real moving matrix of this rotation, of the rotation matrix, that will be derived from frame 0 and frame 1. Okay, because the projected frame is frame 1, while frame 0 is the reference frame. So I will choose among these two is the y rotation. Okay, so if you choose z rotation, you must multiply it at the left side of the stationary matrix. Okay, then if you choose z axis, it will have the same answer if you choose y rotation matrix. Okay, either of the two, you will have the same answer when 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 you get the R03 matrix. Okay, if you multiply this to the if you multiply the derive R01 to the R12 and R23, you will still get the same answer. Okay, so now I've chosen y rotation. Okay, I will derive the stationary matrix. Okay, so based on the direction the directions of axis at the frame 1. Okay, we will form it will form this stationary rotation matrix. Okay, so x sub 1 is the x sub 1 is only projected on x sub 0, while y sub 1 is only projected on z sub 0, and z sub 1 is only projected on uh y sub 0. Sorry, y sub 1 is only projected on z sub 0, while z sub 1 is only projected on y sub 0. Okay, so what we will do here now, we will multiply this, these two matrix with each other in this arrangement. Okay, so we may do it in MATLAB, or we will do it manually using the rules of uh, 3 by 3 matrix multiplication. Okay, So before I do the 3 by 3 matrix multiplication, I will assign the subscript 1 to our y rotation joint variables theta. Okay, because we are getting this from frame 0 to frame 1. Okay, where the joint variable is theta 1. Okay, I hope you understand. So this is theta 1. That's why this is also theta 1. Okay, so we will do 3 by 3 multiplication of, sorry, we will do the multiplication of 3 by 3 matrices. Okay, so the rules of multiplication of 3 by 3 matrices. So if you forgotten, kindly review. So the rules of 3 by 3 matrices multiplication. So the first element of our 3 by 3 matrix here will came from the row, okay, the row times the elements of row 1 multiplied to the elements of column 1 at the second rotation matrix. Then the element of the second element of the first column will came from the second row, then multiplied to the first column of this matrix. Then the last element will came from the multiplication of the third row to the first column of this 3 by 3 matrix. So let's do that. So 1 times cosine theta plus 0 times 0 plus 0 times negative sine theta 1. So we will have cosine theta 1. Okay. Next. Okay. So again, 0 times cosine theta 1 plus 0 times 0 plus negative 1 times negative sine theta 1. So it is sine theta 1. Next, 0 times cosine theta 1 plus 1 times 0 plus 0 times negative sine theta 1. So we will get 0. Okay. So we will go now to the second column. Again, we will repeat that at the first row. Then we will multiply it to the second column of the second matrix. So 1 times 0, 0, 0 times 1, 1 times 0 plus 0 times 1 plus 0 times 0. So we will get 0. Okay. Next. So 0 times 0 plus 0 times 1 plus negative 1 times 0. So it is 0. Okay, next. Third row. So 0 times 0 plus 1 times 1 plus 0 times 0. So we will get 1. Okay. Then for the third column, we will repeat it from the top of the first 3 by 3 matrix. Then the last column of the second 3 by 3 matrix. So 1 times sine theta 1 plus 0 times 0 plus 0 times cosine theta 1, we will get sine theta 1. Okay. Next. Second row. Then 0 times sine theta 1 plus 0 times 0 plus negative 1 times cosine theta 1, we will get negative cosine theta 1. Okay. And finally, 0 times sine theta 1 plus 1 times 0 plus 0 times cosine theta 1, we will get 0. Okay. So that's the rotation matrix of R01. This will be our final answer for R01. Okay, next for R02. Okay, sorry, for R12. We are now at the second rotation matrix. Okay, so first we will look at the location of the joint variable theta. So the next joint variable theta is theta 2. Okay, so our moving rotation matrix will have joint variable theta 2, and the joint variable theta 2 is at the z sub 1 axis. So we will use z rotation. Okay, we will use z rotation to be used as the moving rotation matrix. Okay, so for our stationary matrix, as you can see, class, the frame 1 axis has the same directions as the frame 2 axis. Okay, so it means we will derive a I we will derive an identity matrix based on the directions of axis of these two frames. Okay, so because we have here an identity matrix, so identity matrix multiplied to the z rotation matrix, we will get the z rotation matrix as the answer for R12. Okay, so this will be our R12. So I forgot to mark or label each theta with 2 because we are now at joint variable theta 2. Okay, so don't forget that. So theta 2. So don't forget to put labels on your joint variables. It will be very useful if you use programming languages like MATLAB and Python. Okay, so this will be our R12. Okay, next for R23, R23 like R12, okay, have frames with axes that are at the same directions. Okay, so theta 3, okay, our next or our last joint variable is at say sub 2 axis. So we will use again z rotation. Okay, so I will just copy the sorry, I will copy R23. Okay, for our R23. Now we are at the joint variable 3. So again, this is identity matrix multiplied to moving matrix. Okay, so our answer here again is the z rotation matrix. Okay. Okay, so this is our R23. So our final answer will be the product of these three rotation matrices. So you may use MATLAB to get the product of these three rotation matrices in this order. Okay, so don't forget, don't change the order. So the first one will be R01, then R12, then lastly R23. Okay, so that's all.